Hello everyone, welcome to LICD Lecture 37A. Today we are going to discuss frequency response of Opamp in closed loop configuration. Last lecture we have seen the frequency response of Opamp in open loop configuration. Now let's revise what is frequency response. So frequency response tells us how does the gain of an amplifier responds to different frequencies. Basically, it's a plot of voltage gain in dB versus frequency. So let's build up on the frequency response for an op-amp in a closed loop. Now, op-amp into consideration over here is IC741, and a study of closed loop frequency response is very important, and thus we are investigating it. Okay, so let us start. Let me just adjust my screen. Just a sec. Okay, let us continue. So we have already seen the frequency response of 741 in open loop, and this green color line is that evidence of that. Okay, we have derived each and every point from it, and we have seen how with different gain, how and with increase in frequency, how does the gain falls down at a rule of rate of minus 20 dB per decade. Okay, so with this, we'll start with analysis for the frequency response, for the closed loop. Now, the first definition is of bandwidth. Now, let us see what is bandwidth. So, bandwidth is defined as the range of frequencies over which the gain remains constant. Now, which gain? Gain of the amplifier. Now, a very important observation is this point number two, the bandwidth and the gain. Now gain can be closed loop gain or the open loop gain, are inversely proportional to each other. I repeat, bandwidth and gain are inversely proportional to each other. That means what? If the gain increases, the bandwidth will decrease, and if the gain decreases, the bandwidth will increase. Now, point number three is, with negative feedback in Opamp, the gain decreases, but at the same time, the bandwidth increases. Now, a very important point number four coming up. It says that the product of closed loop gain ACL and the closed loop bandwidth BWF is same as the product of open loop gain AOL and the open loop bandwidth BW. Mathematically, we can write ACL into BWF is equal to AOL into bandwidth BW, which is a very important equation number one. Now, for IC741C, the open loop gain is 2 into 10 raised to 5, and the bandwidth is 5 Hertz. Now, if I multiply this number AOL into bandwidth, I will get 1 megahertz, and that is what we call it as a unity gain bandwidth, also denoted by F of t, FT. So at 1 megahertz, we have seen that this green color curve at 1 megahertz, the gain of the Opamp 741C is unity. Hence the name unity gain bandwidth. So whenever this green color, that is the open loop frequency response, crosses this x-axis, touches this x-axis. Now x-axis is basically 0 dB. That means gain of 1. Okay, any point on the x-axis, and this all these curves which are the closed loop frequency response, that is a blue color, pink color and the yellow color, are the closed loop frequency response. All of them merge together with the open loop frequency response, and they meet at a common point, that is at 1 megahertz. Okay, now let us analyze some circuits in detail. Okay, let me adjust the font for this, and then we can continue. Okay, so let us analyze circuit number A. Actually, we are referring to all the circuits together, but we will go one by one. So let us start with circuit number A analysis. Okay, this is like, yeah. So in circuit number A, we have, it's basically, if you see intuitively, it's an inverting amplifier with feedback resistor RF1 of 100K and R1 of 100 ohm. So the closed loop gain, we know it is given by minus RF1 divided by R1. That will be, the closed loop gain will be 100K upon 100, which will be minus 1000. Now, if you convert this gain into dB, I will get 20 log to the base 10 of 1000, which will be 60 dB. Okay, and if I wish to mark this point on the curve, this will look like this. Okay, in this curve we have 60 dB line, and that 60 dB line will remain constant for most of the time, and when it goes to 3 dB down, we measure that frequency, we will come back to this point. Okay, that frequency will come out to be 1.4 kilohertz, and then this curve will merge with the open loop frequency response. Okay, we'll come back to this point. Fine. Now let's go to the circuit number B. Okay, let us open that and keep it ready. Okay, for circuit number B, the difference is the R2 register is of 1 kilo ohm. In previous case, it was 100, now it is 1K. For circuit number B, the closed loop gain is given by minus 100. Okay, that will be 100K divided by 1K, right? And the mod of it will be 100. So in dB, we have 20 log to the base 10 of 100, which will be 40 dB. And this 40 dB is marked over here as pink color, and its cutoff frequency we will soon find out, it will be 14 kilohertz, and thereafter it will join the open loop frequency response curve. Okay, this was about the circuit number B. Now in circuit number C, its RF3 is 100K and R3 is 10K. So the closed loop gain will be minus RF3 divided by R3, which will be 100K divided by 10K, which will be minus 10. And if we take this in dB, you will get the closed loop gain in dB will be 20 log to the base 10 of 10, which will be 20 dB. So this is marked as in yellow color line, and its cutoff frequency will be 141.4 kilohertz, and thereafter it will join the open loop frequency response. Fine. Now let's come to the frequency response over here clearly. I need to adjust this properly so that it fits. Yeah, it's fine now. Now let us go back to the theory topic. Okay. Now let me adjust this also properly. Yeah, it's properly adjusted now. Now referring to point number 7 we are discussing now, referring to the circuits A, B and C, we can comprehend the following points. That means we can understand the following points. Fine. So equation number 1 is this: ACL into bandwidth with feedback is equal to AOL into bandwidth without feedback. So as per equation number 1, no matter what values of resistors, now we see over here, no matter what is the value of resistor RF1, RF2, R2, R1, RF3 and R3, are product of ACL and the bandwidth must be equal to FT, that is unity gain frequency, which is 1 megahertz. Now, if the resistor values, now let's concentrate on circuit number 1, correct? So if the resistor values R1 and RF1 are set for a gain of 1000, that is a closed loop gain of 60 dB, ACL will remain constant until it reaches your closed loop break frequency F1. Okay, so let us come back over here. That is what we are discussing. This will remain 60 dB almost constant, and it will remain constant until it reaches a cutoff or a closed loop break frequency of 1.4 kilohertz, and this will happen at 3 dB down. So maybe around 57 dB, you will get exactly this closed loop break frequency. F1 is given by 1.4 kilohertz. Okay, and at f equal to f1, your closed loop gain will be 3 dB down. That's as I have mentioned over here. So 3 dB down will be 57 dB, or it will be the 70.7% times the maximum value of ACL. Okay, so thereafter, after this cutoff point has reached, the closed loop and the open loop curves superimpose and they decrease together to unity at f equal to ft. That means what? After this f1 equal to 1.4 kilohertz, this blue color line will merge together with the green color, which is the open loop, and they will decrease together at a rate of 20 dB per decade, and they reach at the unity point, that is 1 megahertz. At 1 megahertz, the gain will be 1 unity. Now let's go to the next circuit. So if the resistor values R2 and RF2 are set such that the closed loop gain is 100, that is in dB it is 40 dB. So let us go back to the circuit. So this is marked in pink color. So the closed loop gain will remain constant until it reaches your closed loop break frequency F2, which is 14 kilohertz. Okay. Now at f equal to f is the signal frequency. At signal frequency equal to f2, my gain, the closed loop gain will be 3 dB down. So maybe around at 37 dB, you will measure this value of f2, this closed loop break frequency. Thereafter, your open loop gain, open loop curve and the closed loop curve will merge together, and they will decrease together towards unity. That is what is exactly happening over here. After this F2, that is the closed loop break frequency, your closed loop curve and the open loop curve will merge together. Fine. Similarly, for the circuit number C, if R3 and RF3 are set for a closed loop gain of, I think there is a mistake over here. It should be closed loop gain of 10. Okay, my mistake, it is written 1000. So R3 and RF3 are set such that the closed loop gain is 10, that is around 20 dB. So your closed loop gain will remain constant. Let us see over here. It is marked in yellow color. So this closed loop gain for a gain of 10 will be almost constant until it reaches the closed loop break frequency of 141.4 kilohertz. Okay, at f equal to f3, your closed loop break at f equal to fb, your closed loop gain will be 3 dB down. That will be at around 17 dB. Correct. Thereafter, after f equal to after f is greater than f3, what will happen is this yellow color curve will merge together with the green one. That means the closed loop and the open loop curves will merge together after your cutoff frequency. Okay. Now, actually, yeah. So the next point will be point number E. The open and the closed loop curves here are there. Okay. Okay, it has decreased a lot, and this has increased a lot. Let us check 17. Yeah, this is proper. So the point number E says that the open loop and the closed loop curves superimpose beyond the break frequency or the cutoff frequency. Okay, so they will superimpose beyond the cutoff frequency. So in case of when the gain was 1000, the blue color curve merges after f1, and when the gain was 100, the pink color curve merged together with the green one after f2, and for the yellow color curve for the gain of 10, it will merge together after f3 with the green color. That is the open loop frequency response. So this happens because the gain into bandwidth product is a constant. Okay. So now next is, let us summarize on these findings in the form of a table. So before going there, let us try this out in LTspice and let us check whether we are getting it or not. Okay. So I have opened up the LTspice workspace window. So here I have made the three circuits with a gain of minus 1000, minus 100, and minus 10. So let us simulate this and check what happens. Okay, so I'll plot gain of 1000, gain of 100, and gain of 10. Okay, so this is my magnitude as well as phase plot. I'll remove it. Okay, we are getting something. And now if I want to compare it with the open loop frequency response, what I will do is I can copy this circuit up, and maybe I can drag and drop over here somewhere. Yeah, so I think this will be fine. I will remove all of this together because you have applied a common V. Okay, so this is the open loop configuration, and these three are the closed loop configuration, right? Now let us check the response once more. Let me close this. Yeah, this is what we were getting, right? And now if I check the open loop response with that, it will merge together. Let's see. Yeah, you see they are merging together. But I think I have to change the frequency range over here. Let's say I'll make it 0.1, maybe 10 points per decade. And now if I simulate it, I might get the curve which I'm expecting. Yeah, yeah, correct. So if I minimize this, so this light blue color curve, or we can say this is the open loop frequency response. The red one is for gain equal to 1000, the blue one is for gain equal to 100, and the green one is for gain equal to 10. So let me minimize this and show this window together. Okay, I will minimize this so that I can show it to you on the side by side whatever we have developed in the theory, and whatever we are getting it in LTspice are one and the same. Actually, how that's how close the ideal and the practical behavior of Opamp is. Okay, I hope that the screen is visible now. So if we can see the curve to your left hand side, which is obtained in LTspice, and whatever curve we have discussed just now are exactly the same. There is absolutely no difference at all. You can see over here clearly. This is the open loop frequency response. Maybe it's not starting at 106 because it's OP07. Here it is 741, and the red color one is same as for the gain of 1000. The blue color curve is for the gain of 100, and it is 40 dB also. You can see 60 dB, 40 dB, 20 dB. Here also we have 60 dB, 40 dB, and 20 dB. Now let's cross check the frequency F1, right? Now F1 is for gain of 1000, that is for red color curve, right? So this is around 60. So after 3 dB down, that is around 57, you should get this cutoff frequency. So I will decrease this. Let me maximize this. I'll decrease this to exactly 57. Okay, let me expand this a little more. 57 will be coming right around. Okay, let me cross check these numbers. Okay, we have a gain of yeah. So we are around 3 dB down, but the frequency over here it's coming slightly different. Let us cross check this. Around 57, there might be some problem. Okay, we'll come back to it, but the nature of the graph remains the same over here. It's very clear from here, correct? So 60 dB curve, it's this. 40 dB, this is 40 dB, and this is 20 dB. Okay, and at around 1 megahertz, it's close to 1 megahertz, we have this. All the curves are merging together. Okay, now let's check. Let's go further. So these were the frequency response demonstration for the closed loop op-amp. I guess yes. Yeah. So these were the key configurations and the open loop configuration. And this is the frequency response which we get. Okay. I hope that this point is clear. Now let us go to. I guess I should try again checking the around 3 dB down, right? Okay, fine, no problem. We will come back to it. We'll go to the next point. Yeah. So these are the values which we are getting over here from the plot. So this is the table which is comparing the open loop and the closed loop gains. So open loop gain is around 2 into 10 is to 5, that is 106 dB. So 3 dB down will be 103 dB. and the bandwidth is 5 hertz. So the gain bandwidth product will be 2 into 10 is to 5 into 5 hertz. That's what we have seen last time. Now let us see right now. So right now the closed loop gain is around you know, let me cross check this once. How does the gain exactly? It's 1.4 kilohertz. Yeah. So let us check that out now. Okay. Yeah. So the closed loop gain over here, it's 1000 for, that means it is a 60 dB, and at 57 dB it will be 708. So basically, I mean we are justifying how we got this 1.41 kilohertz, right? You might be wondering where this number came from. Now it came from here. Okay. Now the closed loop gain at 57 dB, if you do 20 log to the base 10 of 708, I'm sure you will get a number close to 57 dB, right? And the 3 dB frequency directly, it's 1.4124 kilohertz. Now how do we got it? We know that the gain bandwidth product is the same. We know that the gain bandwidth product is 1 into 10 is to 6. So from here we know the gain and bandwidth we can easily calculate, and hence we can calculate the frequency by the formula that gain bandwidth product is given as 1 into 10 is to 6, which will be equal to the gain, which is 708, and which will be equal to the bandwidth. So bandwidth will be the gain, that is 1E6, that is a gain bandwidth product 1E6 divided by 708. If you do that, you will get the number 1.4124 kilohertz. So you can try it out, right? We know for a fact that the gain bandwidth product is the same, and we utilize that fact to do that. Now, probably in this diagram, which is involving, okay, which is involving op07, probably the closed loop gain, sorry, the gain into bandwidth product is not 1 megahertz. Let us try to find out how much it is, and then we can get an idea what was actually going around. So around 0 dB, let us check around 0 dB. Okay, so we are checking a gain bandwidth product of OP07. So it's around, okay, it's very delicate, 760 kilohertz. Okay, so around 760 kilohertz is the gain bandwidth product, definitely. So what will be the cutoff frequency accordingly for OP07? Huh? This table analysis which we have done is for 741. So it was 760 kilohertz divided by 708. That will be close to 1073. Okay, fine, no problem. So I mean we can easily find out this number, these numbers we can easily find out, no problem at all. You can find the unique cutoff frequencies for all. I am saying ki it is different because the gain bandwidth product over here is different, right? It's not at all 1 megahertz, it's lesser than that in fact. Fine. Now let us check that now number. Yeah. So with a closed loop gain of 100, that is 40 dB, if you do 20 log to the base 10 of 70.8, you will get 37 dB, correct? And if you divide 1E6 divided by 70.8, you will get this number, 3 dB frequency, that is 14.124 kilohertz. Similarly, the closed loop gain of 10, that means it is 20 dB. And here the 20 log to the base 10, 7.0, it will give you 7, which will give you actually 17 dB, correct? And similarly you can find the I mean the closed loop frequency or the bandwidth, that is the 3 dB bandwidth or the 3 dB frequency, as 1E6 divided by 708, which will give you 141.24 kilohertz. Okay, so what does all this information reveal? All this information reveal that the gain bandwidth product, rather it would be open loop or a closed loop, it remains a constant number. Fine. And for 741, that number is 1 megahertz. It's 1 into 10 is to 6. So the conclusion over here is, as the closed loop gain reduces, the bandwidth will keep on increasing. So let's say we have a Opamp which is providing a gain of 1000, but its bandwidth is 1.41 kilohertz. right? And now we have a Opamp with a closed loop gain of 10, but its bandwidth is 141.24 kilohertz, right? And in whichever applications where the bandwidth is of importance, we go for a lower closed loop gain. That point should be very, very clear. Okay. And wherever we require a closed loop gain very high, wherein we can sacrifice the bandwidth, we can go for this design. Okay. So the conclusion from this is that as the closed loop gain reduces, the bandwidth of the op-amp keeps on increasing. I guess we have completed today's topic of frequency response of closed loop op-amp, op-amp in a closed loop basically. And we have covered various aspects. We have seen for different gains, how does the frequency response looks like, and how does the open loop and the closed loop frequency response merge together, and why does the gain bandwidth product remains constant at every point of time. That is also very, very clear. And we have demonstrated the same in LTspice also. Okay. So I guess that's it for this lecture. Next time we'll start with OPAM non-idealities. So until then, have a good day and thank you.